Right, so hello everyone, welcome to the 12th week tutorial session for state space approach to control system analysis and design. I am Srishi Siddharth and I'm a TA for this course. So let's begin by recalling the concepts. So in the previous week, we discussed the modeling of a nuclear reactor and we talked about the linearized model of the system. So based on the linearized model, we are going to discuss various types of controllers. So this is recall. So first of all, it would be the linearized model. So the matrices A, B, C, and D depend on the parameters of the nuclear reactor. Discuss periodic output feedback control. Output sampling control. Kalman filter design. This is also all of these are for nuclear reactors, right? Because we have obtained the linearized model. So I'll write this out quickly. All of these are for nuclear reactor. Let's begin. So we'll first recall the linearized model quickly. This model or the state space equation or the state space model. So the first is the matrix A. This is given by minus beta over L star. Zero. Zero eta naught over L star. Beta over L star minus lambda. 0, 0, 0. Gain over tau n. 0 minus 1 over tau n. 0, 0. This is minus kr over tau r squared. This is minus 1 over tau r, 0. And the last row of the in matrix is 0. So remember that. This is 0, 0, 0, 0, 0. So just check if this is a 5 by 5 matrix. And B is, so we discussed this, right? It's all zeros except the last entry, which is Kn. So this is Kn transpose. And we have C. So we have two outputs. So there are going to be 2 rows and 5 columns. The first row is 0, 0 and then 1, 0, 0. So this is 0, 0, 100. It's the third first output. Next output is a linear combination of the third and fourth state. So it will be 0, 0, k r over tau r, 1, 0. Okay. So we saw in the last tutorial, we discussed how to compute the controllability matrix, right? So this is a fifth order system. So the controllability matrix is B, AB, A square B, A cube B, and A to the power 4B. Similarly, the observability matrix. Alright. So to talk about periodic output feedback or fast sampling control, you also have to recall the concepts and how to obtain the discrete model of an LTI system, right? So let's move on. This is the discrete LTI system. Continuous time LTI system. So this is given. We're not considering the matrix D at the moment. And discrete system is discrete time and TI x k plus 1 t. T is the sampling time. This is e to the power 80 x at the previous the current time instant plus integral 0 to t e to the power a tau b t tau times u at the current time instant. So this is the matrix phi of capital T. This is gamma. So we have already discussed in the previous tutorial session on how to obtain the matrices phi of T and gamma. Alright. Now that we have obtained the discrete time LTI system from the continuous time ones, now we can discuss the sampling controllers, right? Sampling based controllers. So the first one is periodic output feedback controller. So what was the main point of this? That the inputs are sampled with formally spaced instants of time. One output sampling period. This means that the control gains are periodically varying. So given an LTI system, we have the discrete time LTI system. And let's say that the sampling rate is 1 over delta. Let's just keep this. Okay, so it's going to be either 1 over delta or 1 over t, right? So t or delta is the sampling time. And then 1 over t would be the sampling rate, right? Or the frequency. So if it's delta, we can write it again, right? This is x at k plus 1 delta equals e to the power a delta x at k delta plus 0 to delta e to the power a tau b d tau and the input at k delta. Similarly, the output would be at k delta because we have the state at k delta, right? So it's c times x at k delta. So the sampling rate is also known as n, I think. Okay. So I'll note this down. The sampling interval t is divided into n sub intervals. Okay, so delta is t over n. So I'm going to erase this. This is 1 over t. T is the sampling time. And at some delta t over n, we have these discrete equations. Also note that in the case of periodic output sampling control, the input is updated n times for each output sample. So the objective is to design the feedback controller, right? Using the periodic output feedback controller approach. So this is the periodic output feedback. Sorry. So on applying the periodic output feedback control gain, so this is x k plus 1 at the next time instant. This is phi delta to the power n plus gamma kc x at kt. So gamma is, I'm just recalling this from the slides on periodic output feedback control. Gamma is phi delta to the power n minus 1 gamma delta, phi delta n minus 2 gamma delta till gamma delta. And the gain k is k0, k1 till k n minus 1. So note that phi, and if you do this n times, so this will be phi delta n is actually phi of t, because t is delta n. G is gamma k. This is the output gain, right? So y is c of x. I think so. C comes from, so this is from the output, and the gain times output is the feedback control. So we choose G and then find K. So what are the conditions on finding the gain K or the existence of solution? It's that the system should be controllable and observable. So the samples is existence of solution of this equation. G equals gamma K. Current system should be controllable and observable. And the number of intervals t should be selected such that n is greater than equal to mu. And for n equals mu, gamma is unique. Okay, so what are the steps? So revision. Step 1 is choose t. So either choose t or maybe t is given in the question. So there are two options. Either t is given, choose some sampling time t. So this is in seconds, right? Then step 2 is, so once we have found t, we can find the discrete time system. So we have evaluate phi at time t and gamma with sampling time t. Step 3 is choose G such that phi t plus Gc has desired poles with negative wave parts, or maybe just has the desired equation of poles. So that would be positive as desired location of force. So now we're talking about a discrete system. So we're not talking about whether the real part is negative or positive. We're talking about whether the magnitude of force lie inside the unit circle, right? Because we're talking about discrete time radial system. Okay. This is as the desired location of force. Then step 4 is, so you have T, now you need delta. So choose N and calculate T over N. Once you have delta, we need to find out phi of delta, phi sub delta and gamma delta. So then we can find out gamma to phi delta n minus 1 is 2 gamma delta, so on till gamma delta. So example, for n equals to, what's gamma? This is phi delta, this is 2 minus 1, 1, and then gamma delta, right? Which was, and then n minus 2 was 0. So for n equals 5, which is the case for the, okay, so we have to actually get to the point of designing the control for nuclear reactor. Then if the system is controllable and observable and we have chosen n to be equal to mu, then we can compute gamma inverse. Compute gamma inverse and find k equals gamma inverse g. So we discussed a question in the last tutorial about finding out the controllability of a nuclear reactor. So we'll use the same parameters and then design the periodic output feedback control for that system. So next, just a second, I'll pull it down. Also in the previous tutorial, I discussed about the Kalman filter solution. So I made a mistake in the, I think in tutorial 10 and talked about the solution of the algebraic Carty equation, it would be symmetric or not. So I have clarified in tutorial 11 that the solution of the algebraic Carty equation for the Kalman filter is symmetric. And then I solved the question, so you could look at that first. Alright. So the parameters were the output feedback, periodic output feedback controller. Parameters. So I'm going to write down the parameters. You have already found out the A and B matrices, and then I'll write those down as well. So it's beta equals 0.005 before eta naught is 2 and Kn is 10. Okay, so this would help us to find the system matrices. And for periodic output feedback controller, we also need the time period to get the discrete system. So let's say t is 1 and the number of period, let's say n is 2. Delta is 0.5. So the matrix A is minus 50, 0.04, and this is 50 minus 0.04, and then the last row is 0. This all zeros and the last entry is Kn. Kn is 10 to the power minus 3. C is the first output is the third state, so it is 0, 0, 1, 0, 0. Then we have 0, 0, 2, 50, 1, 0. Check last and the rank of the controllability matrix. Yeah. So the system was controllable. Okay, so the pair AB is controllable. And to design the output feedback controller, the system should also be observable. So you can check that. So check whether C is observable. So we have the matrices. Now let's find out. Let's go to, so we have T. So we have to evaluate phi of T and gamma of T. Alright. So phi of T is e to the power et. T is 1, so this is simply e to the power a. Alright. Gamma of T is 0 to T e to the power a tau b d tau. This is 0 to 1. We have a, so this is a tau. Then b is, sorry, like this down in the waveform. 0, 0, 0, 10 to the power minus 3 d tau. This is a bit difficult to solve. Just a second. Okay, 1 second. Mm. So we have I, T, and C. Mm. Okay, so we have there are two parts to this question. Find in gamma. Okay, and then choose G such that the closed loop system was phi t plus GC has desired eigenvalues or desired poles. Okay, so we have to calculate phi of t. This is exponential a. See, this is 5 by 5 identity matrix plus a plus a square by 2 factorial and so on. So have you done this in the assignment? How did you find out exponential of a? So this is a fifth order system, right? So this is a big matrix. So has anyone solved the question in the assignment? You can write down your answers in the chat if you are unable to unmute yourself. So let's see what's the dimension of G here. Let's see. This is has to be phi t plus GC. So phi is going to be 5 by 5. C is 2 by 5. 5 by 2. Okay. So 5 rows and 2 columns. First we have to calculate phi t. So what did you do? Did you find it out in MATLAB or did you compute the exponential using the series? You have to calculate terms, right? So reproduce. This is one option, or we could diagonalize the matrix. So let's say the diagonal matrix is lambda. Then e to the power a would be n inverse. So n is the model matrix. And we have to calculate the roots of a fifth order polynomial of fifth order characteristic equation. Okay, so have you done this question assignment? How did you find phi of t? Sorry, phi sub t? Anyone? You can write it in the chat. Okay, so I had done the formula for phi t. This n to the power 6 minus 0, 0, 0, 0, 0.0083 plus 3.5873, and then there's the third one second. 0.0818 minus 3.5873. And then the last row is zeros. So you can check this. So we already have C. C was 0, 0, 1, 0, 0, then 0, 0, 450, 1, 0. KG was 0, minus 4.2 minus 0.5 minus 0.2, 0, 1.1, 0.1, minus 0.10. Then let's compute pi t plus gc. So I'm going to do this just a second. This is 0, 0, 1, double 0, 0, 0, 250, 1, 0. Just a second. Okay, so this is 10 to the power 6, zeros, then 0, 0, I think it's the same as the matrix A because it's 10 to the power 6, right? So answer is 0, 0, 0, 0, 0. And then the eigenvalues of let's see. So the eigenvalues are 1.0269 minus 0.002, 0.3303. So this is greater than 1, right? So I think we should G such that lambdas are inside the unit circle. This is approximately equal to phi of t because e to the power a is of the order of 10 to the power 6. So we should choose some other sampling time. Okay. So if t is 0.5, then phi of t is e to the power 80. This is e to the power 0.58 and this is equal to 10 to the power 6, 0, 0, 0, last row this is 0. Okay, so this is phi of t and this is 10 to the power 6. So phi t plus gc is still phi of t and the eigenvalues are 0.8825, 0.0821, 1, 0 and 1. Okay, so phi t plus gc has desired eigenvalues, desired poles. Okay, so let's see the next step. So choose n and calculate delta. This is step 4. Say n is 2. So delta is t over n. This is 0.5 over 2. This becomes this is 2.58. This is 0.25. Next step is to evaluate phi delta and gamma delta. And for n equals 2, we already have an expression, right? This one. So gamma is phi delta gamma delta. Then it's gamma delta. So pi delta is e to the power a delta, which is e to the power a 0.258. So let's calculate that. This is 10 to the power 5, 0, 0, 0, 0.0807. So it's the only the last column. 0.9193. In the second row, then 0 again. This is minus 10 to the power minus 4, 4 and 0. Last row is zeros. Zero to delta e to the power eta b theta. So we have dv, this was 0, 0, 0. Then was km, 10 to the power minus 3. Okay, so let's see. Just a second. Let me think about how to integrate the exponential. So if you have any suggestions, then let me know. So use so D in this case is 0. So which means now to get the 74. Sorry, 0 to delta. So we have eigenvalues of A. Let's see. Okay, so eigenvectors of this is a okay. So I have the model matrix. This is inverse M inverse. Let me see. So the transformation is uh, lambda is given as M inverse AN. This entire A is M lambda M inverse. You can check in the assignment whether the matrix A has unique eigenvalues, and it's a simple tangent matrix, right? Okay, so this is the matrix. We can find out an inverse. And the diagonal matrix is these eigenvalues. We can find out capital e to the power capital lambda. So it's um, 0 to delta is 1 to 5 to the power lambda tau. And we have m inverse b. So let's make this. This is gamma delta. And let's simply gamma is have to multiply these two matrices, and then it's gamma delta. So I think there's a similar question in the assignment in which you have to find out gamma. And the value of n is, let me check. So n in that case is 5. So what would be gamma? So the general expression is pi delta n minus 1. So this is 4, then 3, 2, simply delta gamma delta, and then gamma delta. This is for n equals 5. Let me check if this is correct. We got the steps again. This is correct. And then similarly, we can find out K, right? So K is, once we have G, this is gamma inverse G. So let's see if we can compute gamma inverse. So for n equals 5, this is gamma, right? So let's compute the dimension of gamma. So gamma delta is phi delta is 5 by 5 and gamma delta is going to be 5 by 1. So we have 5 by 5 and 5 by 1. This is 5 by 1. This is 5 by 5. So gamma is a square matrix of size 5 by 5. And then we have also assumed that n is mu, which implies that gamma is invertible. So we can compute gamma inverse. Gamma inverse is also going to be a 5 by 5 matrix. Then let's see what's the dimension of K. So this is 5 by 5 and G is, so I think 5 by 2. This is going to be 5 by 2. So this means K is going to be K0, K1, K2, K3 and K4. And each of this is going to be have 2 points, right? So this is K01, K02, D. So if you have to find out K0, you just have to write down this row vector. And then the same for all row. So K4 is K41, K42. So these dimensions are fixed because we are talking about an nuclear reactor and we have fixed number of states, that's 5. We have 1 input and 2 outputs. Okay. So this does involve a bit of a computation, but after that you know how to find out K and gamma. Alright. So let's move on to the next topic, which is fast output sampling control. So this is, I guess, fourth. Let's recall a concept about this controller before moving on to the design for the control for nuclear reactors. The first one is that all the outputs are sampled at the same rate. The same rate, and that rate is n. This means that the controller is non-dynamic. So the input sampling period is T. Output sampling period is delta, which is T over N. For sampling rate 1 by T, we already know the discrete system, right? Or 1 by x at k plus 1t was phi t x kt plus gamma t u at kt. And similarly, the output. Assuming d to be 0, then it would be for delta, right? So for 1 over delta, uh, k delta. So choose F. So this is the state feedback gain. That. So what's the closed loop system? The closed loop system. So this is state feedback. We did output feedback in the periodic controller. In this we have state feedback. This is phi t plus gamma t f. The closed loop system should be stable. Should have desired eigenvalues. And what's the restriction? There should be no pole at the origin. So then we calculate L, right? So the FOS controller gain is given by LC equals F. So we have chosen F. C is for the nuclear reactor. C is given by C0 plus TF phi T plus gamma TF inverse. So we know what C0 is. C0 is C phi delta and C phi delta square till C phi delta n to the power. So it's phi delta to the power n. D is not the one from the system matrix D, which is a relationship between input and output. D is something else. So D is C gamma delta, then C phi delta gamma delta plus gamma delta. Sorry, C gamma delta. And then function J equals 0 to n minus 1. Gamma delta. This is C and C0 and D. Then we can calculate this first term. And we already know the closed loop system matrix phi t plus gamma tf. So once we have C, we can find L. So L can be obtained if C inverse exists. In this case, L is simply f C inverse. When does C inverse exist? C inverse exists when C0 plus df and phi t plus gamma tf are invertible. So let's write down the steps. Choose t. And step 2, find phi t and gamma t. Step 3, choose f. Replace the poles. Phi t plus gamma tf at the desired locations. Choose choose n, and therefore delta is t over n. You have to calculate phi delta, gamma delta. What's the next step? We have phi delta, gamma delta. Then we find C0. And D. Step 7, find C and check if it is invertible. Step 8, L, right? So find L equals F C inverse. Okay. So for the nuclear reactor, let's talk about the dimensions of the various matrices. So phi T is 5 by 5. So for the nuclear reactor, T is going to be 5 by 5. Then gamma T is 5 by 1. Then F is going to be, so this is 5T plus gamma TF. This is 5 by 5. This is 5 by 1. This is 1 by 5. So F is going to look like some F1, F2, F3, F4, F5. Yeah. Then choose N. So let's say N is 5. So then we find phi delta and gamma delta. So phi delta is again 5 by 5. Gamma delta is 5 by 1. We have to calculate C0. So C0 is C phi delta square. What's C phi delta? C is 2 by 5. This is 5 by 5. This is 2 by 5. So this is, each of them is 2 by 5. We have 5 columns. It is going to be 10 by 5. So the first 2 by 5 is going to be 10 rows and 5 columns. So you can extract the first row, right? So again, this is one of the assignment questions. The first, we can calculate the first row of C. Then we have D. So D is for n equals 5. We have, okay, so first row of C0 is first row of C5 delta. So C5 delta is 2 by 5. So the first row of C0 is first row of C delta. So you don't have to compute the whole C0 matrix to find the first row, right? This is the first row of C times 5 delta. So D is for n equals 5, we have J equals 0. And so, okay, let's see the first row of D. So we have C, so on. So C gamma delta is 2 by 5 and 5 by 1. So D1 is, okay, this is also one of the assignment questions. So D1 is the first element of D, which is the first element of C gamma delta. And then you have to complete the whole C0 and then D. Just a second, let me check. Yeah, so C requires C0 plus D times F. Then compute C0 and D to find C. So what's the dimension of C? Let's is C0 plus df phi t plus gamma delta F. So this is 5 by 5. This is inverse. C0 was is 1055. So D should be 10 by 1. D C. We have C delta, right? So C gamma delta is 2 by 1. Okay. D0 plus DF is going to be 10 by 5. And C is going to be a matrix of size 10 by 5 multiplied by 5 by 5. So this is of size 10 by 5. So then you can extract the first row. And I think that's also one of the assignment questions. What's the first row of the matrix C? I have to find out D for n equals 5. So this is C gamma delta. This is C pi delta part D times gamma delta. So let's expand this. This is going to be D C gamma delta C phi delta So C gamma delta is, this is 2 by 5. This is 5 by 1. This is 2 by 1. And D was 10 by 1. So we have 4 more columns of size, 4 more rows of size 2 by 1. Let's see what this is. This is C times 0 to 4. So that's J. You might get typing mistake. This could be J, which is D. I have to check. See, this is pi delta to the power 0 gamma delta. This C gamma delta. C pi delta gamma delta. Simply C gamma delta. Then it's C pi delta gamma delta plus C delta. sorry, C delta, C gamma sub delta. So we had this term, then we had these two terms, and I think it's going to be the three terms. So this is Q as part of phi delta. So C gamma delta is 2 by 1. So we have 2 by 1 here and 2 by 1. Here 10 by 1, let's check. Yeah, so this is of size 10 by 1. Just, I think in the lecture notes, there is a mistake. There should, it's not capital T, this is J. So let me just check once. Has anyone attempted this question in the assignment? So I just want to know, is it phi delta to the power capital T or is it J? Because then there is no index in the summation, right? I'm talking about this one. Should this be J? I think this is J. I'm also seeing the derivation of this. Then this is C slide 28 or lecture 29. So a derivation of L. So this is not capital D, this is J. So this is the correct expression for D. So what you can do is, once you compute C gamma delta, that's fixed, right? This is used everywhere. So here in all of the 5 entries. And once you calculate this, this is also used in the subsequent entries. And then you can just compute phi delta square, phi delta cube, and phi delta to the power 4. It's the Karma filter design. So if you have any questions, just let me know. Let's move on to the next topic. This is This is an optimal estimator. We have already discussed about how to find the solution of the optimal gain, right? Using the algebraic part equation. So what does it minimize? If it's an optimal estimator, it optimizes something, okay? So it minimizes the mean of the squared error. So it works on the principle of function of prediction. There are two stages. It predicts and then it corrects it. So there are two stages. Prediction stage and the correction stage. So we have the system model, right? So it's x dot equals x plus bu or in the discrete time case. So this stage produces an a priori system estimate, system state estimate, previous state. So we have the previous state. By using the system evolution prediction model. Okay. So the prediction state produces an estimate. And now correction stage. So we also have a measurement system, right? Y equals Cx. So the correction stage takes into account the observation. Uses so to produce story. This is story state estimate by correcting the estimate in the prediction stage. Okay. So we have already seen this, right? So we have the system model and then there is input and output one. So in the discrete time state, we have xk, so it's fk minus 1 xk minus 1 plus gk minus 1 uk plus wk minus 1. So this is the deterministic part. Similarly, you have an output equation, right? Or the measurement model. This is the process model. The measurement model. The output y at k is hk xk. Then the output noise. This is vk. So again, We know this, so this is deterministic. So let's recall the Kalman filter equations. So we have the system model. First one is that we predicted, right? It's a prediction stage. So predicted state is xk tilde is phi k and k minus 1 x hat k minus 1 plus gamma k minus 1. Then we have to predict the covariance matrix, right? The state covariance matrix. This is predicted state error covariance matrix with the covariance matrix P. Is P, and we're talking about the prediction state, so it's dimension k. This is phi k minus 1, P at the previous dimension, k minus 1 plus qk. So this has to be chosen. Okay, then we find out the Kalman gain. This was the prediction stage. Then we find out the Kalman gain. K at time instant k. This is P delta P tilde k H k transpose. This is from the measurement. H k P tilde k H k transpose plus R k inverse. So how should we choose R k such that we have an inverse of this matrix, right? This is chosen. Okay. So we have predicted, then we have the Kalman gain, and now we have to correct the estimate, right? So this is corrected state. First of all, it's corrected state covariance. This is simply P of P circuit. This is I minus K at time instant K, H at time instant K times the predicted P at K. And the corrected state is X without the tilde, it's XK is X tilde K plus the Kalman gain K, and this is the error between the measurement y and H at K, X tilde at K. So no, Q and R should be chosen to obtain the desired transient performance of the field. So that's it for today. If you have any questions about the assignment or the tutorial, then please let me know. If not, then you are free today. Please go ahead. If you can unmute yourself, that's fine. If not, you can write in the chat. Yeah, I can hear you. Sorry? Yeah. You need inverse Laplace to find? What do you need to use inverse Laplace for? Ah, okay. So you want Laplace inverse of Si minus A inverse, right? Yeah. So, okay. So Si minus A is a matrix of size n by n, right? And A can have any form. A does not need to be triangular. So there are going to be elements of A. Let's say for a second order system. A1, A2, A3, A4. Okay. These are constants. Si minus A would be S minus A1, S minus A4, minus A3, right? You can take the inverse of this matrix, right? This is a 2 by 2 matrix. You calculate its determinant. This is Si minus A. So this is the inverse. Okay. So for example, one of the entries is going to look like S minus A4 upon determinant of Si minus A. This is S minus A4. So it's a second order system, right? So S square plus some B1S plus B0. So you can have factor it into roots. Let's say S minus, what is it? S minus V1, S minus V2. So you have to take the Laplace inverse of this. It does not matter whether the matrix A is lower triangular, upper triangular, or diagonal. It can have a general form. You have to find the Laplace inverse of individual entries. Yeah. The random one is this one random mod or is it random mod matrix? One second. Yeah. So it's when you have yeah, it's when you have distinct eigenvalues, then you can do that. Yeah, yeah. So yeah, if you have lambda one distinct eigenvalues, then the model matrix is a random one. You can read about this one second. Let me check. Yeah, I think it's for distinct eigenvalues. So I did the question for distinct eigenvalues, right? When you have distinct eigenvalues, you can form that whole matrix. So this would be the model matrix, and then you can use this to diagonalize the system. We just talked about this, right? So lambda, the diagonal matrix would be, I think M inverse or something like this. This is lambda one, lambda two till lambda n, and this M matrix is the random matrix. I'm not sure about that. Sorry, you can ask on the Q&A forum. The professor, I think, will answer you. Yeah, thanks. This is for distinct eigenvalues. Then we can invert this and diagonalize the system. Yeah. Okay. Alright, so if you have no questions, you are free to leave. That is fine. No, thanks.